Hello everyone, welcome to Maths with Math Tips. In this video, we discuss about solutions of linear partial differential equation. So in the last video of partial differential equation, we already discussed about the types of PDE, the linear PDE and the non-linear PDE and their identification. So in this video, we are basically solve the linear partial differential equation. So let's start the video, and before starting the solution, I am requesting you to all those who are new in my channel, please like the video, comment if you have any doubt in the comment section below, and don't forget to subscribe the channel. A linear PDE of the form PP plus QQ equal to R. So this is the general form of the linear partial differential equations, where capital P, Q, R are the functions of x, y, z, and small p stands for the first order derivative partial derivative with respect to x, and small q stands for the first order partial derivative with respect to y, and this z is the dependent variable of the variable x and y, where x and y are the independent variable. The general solution of equation number 1, suppose this is equation number 1, pp plus qq equal to r, is given by phi of uv equal to 0. This is let us take equation number 2, where phi is an arbitrary function and u xyz equal to c1 and v xyz equal to c2 are two independent solution of the arbitrary equation this. Dx by p plus dy by q plus dz by r, this is known as Lagrange solution of the linear partial differential equation. So there are mainly four types of problems, that is four types of Lagrange solution. So before going to the types of solution, we first note how to solve this type of equation, that is the solution procedure of the equation, that is working rule for solving pp plus qq equal to r, that is Lagrange equation. Now first step 1, the given equation, linear equation, put in the form of pp plus qq, this is equal to r, and then we identify the p, capital Q and capital R. Then write down the Lagrange auxiliary equations. This equation dx by p plus equal to dy by q equal to dz by r is known as Lagrange auxiliary equation. So first our work is put in the form pp plus qq equal to r, then write the Lagrange auxiliary equation dx by p equal to dy by q equal to dz by r. Then step 3, taking two ratios, this is a ratio, this is a ratio, and this is a ratio. There are three ratios. So taking two ratios at a time, and by using the method of ODEs to obtain this u xyz equal to c1, that is a solution, and v xyz equal to c1 are two independent solutions of dx by p equal to dy by q equal to dz by r. Then step 4, the general solution of pp plus qq equal to r can be written as phi of uv equal to 0, then u and v are u xyz equal to c1 and v xyz equal to c1 equal to 0, or u equal to fv or v equal to 0, or in generally we write c2 equal to fc1 or c1 equal to gc2 or phi of c1 c2, this is equal to 0. This is the to write the solution procedure of the equation pp plus qq equal to r. Now we are comes to the first type equation, type 1. This is the type 1. So let us solve the equation y square z. So in these four types of solution, I will basically explain through the example. So first we take the example y square z by xp plus xzq plus y square equal to y square. So if we compare this by pp plus qq, this is equal to r, then capital P equal to this y square z by x, capital Q equal to xz, and capital R equal to y square. So the Lagrange auxiliary equation is of the form dx by p equal to dy by q equal to dz by r. So dx by y square z by x, dy by xz plus dz by y square. From first two ratio, that is these two ratio, we see the variable z cancel out from these two ratio. Z is common variable, so z cancel out, and then we get dx by y square by x equal to dy by y. So we can write this as x square dx minus y square dy, this is equal to 0, and if we integrate, then we get x cube minus y cube equal to constant equal to, let us take the constant as c1. Again taking first and third ratio, that is these two ratio, dy by xz, this is equal to dz by y square. We can write that we see that first and third ratio, sorry, this ratio dx by y square z by x by this ratio, third ratio dz by y square by z, y square cancel out, and we can write dx by z by x, this is equal to dz by 1. This implies x dx minus z dz, this is equal to 0. Now if we integrate, then we get x square minus z square equal to constant equal to c2. So the required general solution is this one c2 and this one is c1. So we can write the general solution by three way. First we can write phi of c1 c2, this is equal to 0, or you can write phi c2 equal to c1, or you can write phi c1 equal to c2. So in this case we are write the solution as in the form of phi of ub, this is equal to 0. That means u xyz equal to c1 and b xyz equal to c2. So this implies phi of x cube minus y cube comma x square minus z square, this is equal to 0, where phi is an arbitrary constant. So this is the type 1 solution, Lagrange solution. Now let us comes to type 2 solution. Suppose that the integral dx by p equal to dy by capital Q equal to dz by r can be obtained easily by taking suitable chosen choice of two ratios similar as type 1. So in first case we just choose the suitable two ratio and then solve then by independently by using ODE, the solution procedure as in same as ODE, and then we just write the those two as in the form of phi of this and this is equal to 0. But in case type 2, in one case you can easily solve the ratio, solve the two ratio, but most of the cases when if we take any two ratios and they are not solvable, then these equations form in type 2 type equation. So suppose and the another integral cannot be obtained by using the same method, then the type 2 equations comes, then one integral is known to us is used to find the another integral. So the one integral which is known to us, we used it to find the another integral. So in the second integral, the constant of the integration of the first integral should be removed. Then we find the second integral by using the first integral, our known integral, and then we remove the first integral. So let us take an example. Let us take xy p plus y square q, this is equal to xyz minus 2x square. So first we write, our first work is to write in the form of pp plus qq, this is equal to r. So capital P equal to xy, capital Q equal to y square, and capital R equal to this. So we write the Lagrange auxiliary equation by dx by p, that means dx by xy equal to dy by q equal to y square, and dz by z, dz by r, that means xyz minus 2x square. So taking first two ratios, that means this and this ratio, y cancel out and we get dx by x, this is equal to dy by y, and we get log of x by y equal to log c1. This log c1 is constant of integration if we take, and this gives x by y equal to c1, that means x equal to c1 y. So this is the first, if we take first two ratio, then we get an integral. But now if we take from the second and third ratio, means dy by y square equal to dz by this, then this is not easy to solvable. Then we put x as c1y, that is we use the first integral to find the second integral. So x, if we put this in place of x, then we get c1y into yz minus 2 c1y square. This is equal to dy by y square, this is equal to dz into this. So this implies c1 into dy, this is equal to dz by z minus 2 c1. So c1 integrating c1y, this is equal to minus log of z minus 2 c1 equal to c2, and this gives x minus, now we replace the c1 by x by y equal to c1 is the first integral. So we put in place of c1, this is equal to x by y. So if we put the value of c1, then we get x minus log of z minus 2x by y, this is equal to c2. Now the required solution is, if we write c2 equal to phi c1, this is an form to write the solutions. So the required general solution, so this is equal to x minus log of z minus 2x by y, this is equal to phi of x by y, where phi being an arbitrary function. So this is the type 2 case 2. Now let us come to type 3, type Lagrange equation. So we may require to write the Lagrange's auxiliary equation, this dx by p equal to dy by q equal to dz by r equal to p1 dx plus q1 dy plus r1 dz by p1 p plus q1 q plus r1 r, where p1 q1 r1 are the multipliers. These are the multipliers chosen carefully. If p1 p plus q1 q plus r1 r, that means denominator this is equal to 0, then we can write the numerator this is equal to 0. And now we just integrate the numerator to get an integral u1 xyz equal to c1, say suppose. So this, now with the help of another set of suitably chosen multipliers, we may obtain the another integral similar as in say above. This is equal to u2 xyz equal to c2. Now sometimes only one integral is possible by use the suitable multipliers, and the other integral may be obtained by methods of type 1 or type 2. Then the required solution is u phi of u1 u2 is equal to 0. That means in type 3 there are 3 cases mainly. So first case is choose two sets of multipliers easily, and second case is choose one set of multipliers and get the one integral, and then in using type 1 or type 2 we get the another integral. Then the required solution is phi of u1 u2 is equal to 0, where phi is an arbitrary constant. Let us take an example. Let us take mz minus ny into p plus nx minus lz equal to q. This is equal to ly minus mx. So Lagrange subsidiary equation corresponding to the given equations are dx by p. P means this function, p, this is q function, and this is r function. So dx by p, dy by q, and dz by r. So choosing the multipliers x, y, z. Here in this problem we are solving this by using two sets of multiplier, and then write the general solution phi of u1 u2 equal to 0. So we write the ratio of 1. This is suppose equation number 1 by choosing the multipliers x, y, z. So x dx plus y dy plus z dz by mz minus ny into x plus nx minus lz into y plus ly minus mz into z. So now we see that the denominator is 0. That means we can also write the numerator is also equal to 0, and then integrating we get x square plus y square plus z square equal to constant, and let us take the constant as c1. Now we get the one integral. We get one integral this. That means u x y z equal to c1. We get the function u1 as x square plus y square plus z square. Next, choosing the multipliers L, M, N as the multipliers respectively, then the ratio becomes, we can write L dx plus M dy plus N dz by L into mz minus ny plus M into nx minus lz plus N into ly minus mx, and in that case also the denominator is also 0. Then we can write the numerator is also 0, and integrating the numerator we get lx plus my plus nz equal to constant, and let us take the constant as c2, and we get the functions u2 xyz equal to c2. Then we write we just write the solutions phi of u1 u2 this is equal to 0. That means phi of x square plus y square plus z square, the first integral, and the second integral this lx plus my plus nz this is equal to 0, or phi being an arbitrary function. This is the third type of Lagrange equation. And let us now come to the fourth order type Lagrange equation, which is in type 3 one set of multipliers p1 q1 r1 we write this is dx by p equal to dy by q equal to dz by r. This is equal to, we can write p1 dx plus p2 dy plus p3 dz by p1 p plus q1 q plus r1 r. Now if we see that p1 dx plus q1 dy plus r1 dz is an exact differential of the denominator p1 p plus q1 q plus r1 r, that means this is the denominator is the exact differential of the numerator, sorry, if we see that this is an exact, this numerator is an exact differential of numerator denominator, then we can write p1 dx plus this p1 dx plus q1 dy plus r1 dz by p1p plus q1 q plus r1 r may be combined with a suitable ratio of dx by p plus d equal to dy by q equal to dz by r, and this will gives one integral. So we get the first integral, suppose u xyz equal to c1, and we have to find the next integral. Now choose another set of multipliers p2 q2 r2. Each ratio equal to, you can write p1 dx plus q2 dy plus r2 dz by p1p plus q1 q plus r2 r. Suppose the numerator is again an exact differential of p2p plus q2 q plus r2 r, then the two ratio a and b, that means this is a ratio b and the above ratio 1a. So this ratio, two ratios a and b are combinedly give the second integral. So let us take an example. The example is y square into x minus y into p plus x square into y minus x cube. This is equal to z into x square plus y square. So this function is capital P, this function is capital Q, and this function is capital R. Therefore Lagrange auxiliary equations, we can write dx by p, dx dy by q, and dz by r. So this is equal to dx by y square into x minus y equal to dy by x square into y minus x equal to dz by z into x square plus y square. Then let us take that first two ratios. We can write dy by y square equal to dy by minus of x square, since x minus y and x minus y cancel out both sides. So we can write this implies x square dx plus y square dy, this is equal to 0, and integrating we get x cube plus y cube, this is equal to constant, and let us take the constant as c1. So choosing the multipliers 1 minus 1 0, each ratio of 1 is equal to, we can write dx minus dy by so 1 and minus 1 are the and 0 are the multipliers, so dx minus dy by y square into, so this is the ratio, so dx minus dy minus 0 into dz. So dx minus dy by y square into x minus y minus x square into y minus x, this is equal to, we can write dx minus dy by x minus y into x square plus y square. Now combining with the third ratio of 1 with this ratio, so let us take the third ratio and this ratio. So third ratio and equate third ratio and this ratio, we get d of x minus y by x minus y minus dz by z, this is equal to 0, since this x square plus y square term and x square plus y square term cancel out from both sides, and if we integrate this term, then we get log of x minus y minus log of z equal to, let us take the constant of integration as log c2. So this gives, we all know that log of x minus y by z is equal to log of c2, this gives x minus y by z, this is equal to c2. Therefore we get the both functions u2 of equal to c2, and also we get this as a function of u1, so u1 of xyz, this is equal to c1. So we get the functions of u1 and u2, or you can take u and b and so on, any other function name. So the required solution is, this is the form u1 u2, this is equal to 0, and u1 means x cube plus y cube, and u2 means x minus y by z, this is equal to 0, where phi being an integral arbitrary function. So these are the 4 types linear PDE, solution of 4 types linear PDE. If you like the content, then please give a like to this video, share with your friends, and subscribe the channel. Thank you friends, see you again in the next video, and in the next video we will discuss the solution procedure of nonlinear PDE. Thank you.